Good evening, friends. Welcome to Eastern Academy, and we are discussing about electronics as a part of embedded system programming. And today is session 3 of the electronics. The last two sessions we discussed about what is electronics and what are the electronic components. Okay, and this session we are going to discuss about the very important component of electronics, that is transistor. So we discussed about types of transistor. The last session we discussed about what is transistor, and this session we are discussing about type of transistors. Why there are so many types? Okay, so before we get into the session, let us review here. What we discussed in the last classes. That will be giving you a good idea. Am I right? So, 1 minute. Okay, so we are very clear about what is electronics. Electronics is nothing but a box, a block, which take electrical signal and which gives out electrical signal. That's all. This is simple. This is all about electronics. But the beauty is this block do not have no manual control. That is what is important. The block does everything automatic. So they need a, see, normally you say in electrical circuits, we have a switch, we have a regulator or rheostat. These two components are variable resistor. We do them in manual. We use the hand to control them. That's why we call manual. So, but in electronics, we cannot use the manual control. So our normal switches or regulators cannot be used in electronics. So what the engineers have found or scientists have found was a component, same switch. Understand? A same switch which is controlled by electrical. See that? Same, there is a variable resistor which is controlled by voltage or current, whatever it is. Both are same. So understand. So electrical control, that is called automatic. That is the beauty of this electronics. How do we implement the circuits or not? We will discuss in coming days, next session and all. But so what electronics important was, see, electronics they have designed long time back. Unfortunately, they could not able to find a component. Only the first component was your transistor. Actually, we draw a symbol like this: base, emitter, collector. But actually, this should be a right symbol. This should have been a right symbol. A variable resistor, a diode. Am I right? This should have been a right symbol. Actually, you are controlling a resistance. That means you are controlling a flow of current. Okay. That's why they call transfer resistance. This will give you a good idea, but this is not exactly the variable resistance. Don't get confused. I'll explain to you that difference between this and the current source. What is variable resistor? What is current source? I'll explain to you that. You normally see in the colleges like this. We don't call this a variable resistor. I'll tell you why it is. I'll explain to you maybe while I'm explaining this. So basically what they were looking for to have an electronics, they were looking for a component. They are looking for a component controlled by voltage or current, whatever it is. There are two types of components. One is called voltage controlled Other one is current control. Each one is having a advantage, disadvantage. That is what we're going to discuss today. So basically there are two inputs. And this is called normally control input. Control input. This is main contacts, main circuit. So you are going to do that. So what you are going to do, you have two types. One is I can use this block as a switch. That means if I give a 0 voltage, switch will be off. If I give 5 volt, switch will be on. That is one. Or I can use this as a variable resistor. That is what we have seen in the last session, how connecting two diodes. Understand one thing? Two diodes in back-to-back. The Bell Laboratory scientists have achieved. Okay. This they call collector, this they call emitter, and I connect a bulb. When I increase the voltage here, I have a resistor. When I change this variable resistor, then the current changes. Because of the current, this current changes. So this becomes brighter thing. At one point, this goes to the maximum. You cannot go beyond that. That's a bulb resistance. You cannot go that. Same way, while initially this diode requires 0.7 volt. Till you give a 0.7 volt, there will not be any conduction. You understand now? So this is what they have transformed, the two diodes. Don't get it deep. You are not a scientist. You are actually an embedded system programmer. You know that this is called abstraction. Please understand the abstractions. We go from bottom, atom.
Excuse me, sir.
Yes.
Sir, that below one is emitter or collector, sir?
Emitter.
Sir, you have written C, sir.
Here. Oh, sorry, emitter. This is emitter. Sorry. That's emitter and collector. Thanks. So this is what the abstraction. You are here. Okay. This is the technologies. The new field. And atom was the basic scientist. How the atom works. What are the energy, how the atom gets energy, how the protons are revolving around that. Those things studies by scientists. Then go by application of scientists. Then go for engineering, application of engineering. Then technologies. In technology itself, hardware. Then get into IC design. Then get into the software design. Then go back. Now, if you say that I have to go from understand from bottom level here, then you're gone. It will take about same period. They have taken about 300 years to do these things. You cannot do the same thing. So you should know that where you have to start. You have to understand all these things. You have to start from here or here. That's the trick. Even here in the technology side, you have so many things. That is, we divide into two groups. Microprocessor. Above microprocessor and below microprocessor. The above microprocessor is microcontroller, embedded system, software. Below microprocessor is digital electronics, analog electronics, components, electronic components. It goes like that. So how are we going to learn? That's very important. You should start from here today. In 2022, you should start from here, not from the atom, not from PN junction. Those things are becoming knowledge. You are not going to work. All the engineering college students are not going to work on a fabrication center or transistor manufacturing place. Understand? So, as I told you very clearly, learn how to use addition, subtraction, multiplication, division. But use calculator. You are in a shop. You are in a shop. You have a product. That product is 693 rupees. Somebody buy about 14 products. Somebody buying about 14 products and your product costs you 693 rupees. You tell him, wait, sir, you take a paper, 693 multiply by 14. You multiply and give a thing. That guy will ask you, the customer will ask you, sir, don't you have a calculator or computer? See, that is a very, very common thing. Everybody will know that in 2002, how do you behave? Am I right? So, knowing this is different and living with that is different. That what I'm trying to tell you now is, what are all the components, how the each components are working. From there, from electrical, electronics, from that digital electronics, from microprocessor. It's a path I'm building you now. It doesn't mean that you have to be 100% perfectly understand about this. 100% no, that don't have time. You don't have time at all. You have very limited time now to go to the job. You have a very limited time now to job. Those things you understand, they will teach you in the college. That time you will get to know that. This course is totally different. So this has been drawn like this. This diode, this is base. Base to emitter is this. So we put like this. So the current goes like this. Understand? And you connect it to ground. And you supply here, then the current. And we have discussed in the last class, here is this small element P and N and P. N. Now you give a current here, that guy is going to give a current through this path. But this is a big area. Understand? Big area. This is a big area, but this is small area. So this current will be small. This current will be big. Like a lever principle. Exactly take a thing. It's like this. I put here, let's say, this distance is, ratio is 1:5. If I pull down this guy 1 inches, okay, this guy will move on to 5 inches because the 1:5 is the ratio. You understand? Now the same ratio here. This one is small, base current. This one is collector. So we call this as a collector current, IC and IB. So there are, let's draw here once again. Then you will understand. So I have two here. The current this way, that is this base to collector, emitter. This current is responsible to produce this current, that is IB, IC, collector current. And based on the size of manufacturers, IC by IB, the ratio will vary. This is not fixed one. If you buy a type of transistor, some 5 types, X, Y, Z and everything, this guy will say that, hey, my ratio is 10. Somebody will say 100. Somebody will say 1000. That depends on the requirement usage. You can buy that. Understand? So the main important thing in every transistor is what is beta. The beta is called IC by IB. IC by IB is called beta, or you can call it the amplification factor. This beta is called amplification factor. Please understand, the current here is not based on only this current, the voltage also. This voltage is the one which is responsible for giving so much of current. Understand that. That's a very important case for us. So the amplification is not actually doing. What this guy is doing is, this guy is making the electron flow, so more electrons could be able to flow through this circuit. And that's a big research. That's what the Bell Laboratories did for so many years. Okay. That is what we discussed in the last class, how exactly Bell Laboratories did the thing. So this is the trick. Then people thought, why not we use this way? That is, I use N material, P material, and N material. Why not I use P material, N material, and P material? People thought use it. No, nothing wrong. But the problem here is, in this case, the base current will not flow like this because this is P and N. So the trick is that
You flow in
opposite direction. That's why we draw like this. We draw like this. Two type of transistors. This we call, here also it called emitter, base, collector. Emitter, base, collector. But this is called NPN transistor. This is called PNP transistor. Here you connect the battery like this. So this current is responsive for this current. Understand? So we have two types of usage. Okay, that's all very, very deep into the analog circuits, which we don't go in there. So you can use anyway. So this is called one. So there's no big difference. One is called NPN. One is called PNP.
PNP.
Okay. Two type of transistors are there. But the problem is, see, they were doing this. They were building big circuits using this. What happened? This guy controlled the current, and this guy is giving the out, and that guy they used to control the other one. So many things. Don't worry about the circuit. I draw a small circuit which is nowhere connected. I'm just drawing it. I'm going to give you some important point. That's why I'm drawing this. Circuit does something. I'm not worried. Then you have to follow that. How this guy, everything. The trick here is this current control this current, and you get a voltage. This guy controls this. This guy control. The problem is, see here, there's a current here, and there's a current here. There's a current here, and there's a current here. But there are so many currents are flowing. But all these currents are given by whom? Your main supply, main power supply. The main voltage battery is going to give you the supply. So what happened? When I have more transistors, there'll be a more current. Understood? Also, if one output goes to so many people and everybody is going to take so much of current. So when I have few transistors, okay. When I start connecting more transistors, what happened? There is a huge current. Okay. We will discuss about right now this. See, understand one thing. You think only one thing. Please understand, this is very important for everybody to understand. Let us take a NPN. And let us assume that the beta of this guy is, the beta is 10. That is amplification factor is 10, we assume now. Okay, so let us draw a small circuit now. Let us draw a small circuit. Beta is 10. And I apply here 20 voltage. I apply here 5 volts, assuming. And this is diode. Understand? This base and emitter, which we already discussed. If you draw the diagram, N, P, N. So this is forming a diode. So this is what we are connecting now. So if you wanted to this to be forward bias, you should give more than 0.7 volt. Otherwise, what will happen? As we discussed yesterday, when you do PN junction, there'll be a small depletion layer. If you want to break, the electrons have to flow. The electron have to push through this and come here. You have to apply a minimum voltage of 0.7 threshold. If you don't apply 0.7 volt, then the electrons will not flow. Now, assuming that I put here 1K resistor. How many resistors? 1K resistor. Okay, and let us assume this is 1K. Now, there are some steps. The steps are very clear. Please, this is a pure electrical. Don't worry about it. This except only one place. It's a pure electrical. Now, you have to, this is called, let us give a name for everything. This is called VB, voltage B at base, VB. This is called IB, base current. This is called RB. This voltage, that 0.7, we call this a VBE. That is voltage between base and emitter. That's actually a 0.7 volt in silicon. In germanium, that is 0.2 volts. Now, you need to calculate IB first. IB is equal to VB minus 0.7 or VBE divided by RB. Understand that? You draw only that circuit. I have a diode. This is what the equivalent. This is IB. You understand now? This is 0.7 volt. Sorry. So this is RB.
Sir.
Ah.
Sir, what about that amplification factor?
That will come next. That is next. First of all, you calculate IB. Okay. Once you calculate IB, what is IB now? I have given 5 volt. So 5 minus how much? 0.7 divided by IB is equal to 5 minus 0.7 divided by 1K is equal to 4.3 divided by 1K is equal to 4.3 milliampere. You understand now? 4.3
yes,
milliampere is a current here. Now, the 4.3 milliampere. So let me give a bigger voltage here. Let's give about 100 volts. Otherwise, there'll be a small different discussion. Now, when I see 4.3 milliampere, that is IB. Then now IB is, now we found out IB is equal to 4.3 milliampere. What is the equation? IB is equal to, this is the equation. I write it here. IB is equal to, maybe my video I'll, okay. IB is equal to VB minus VBE divided by RB. Now you calculated that is 4.3 milliampere. Now, this is the first step. Second step is IC. IC is equal to beta into IB. Understand now? That is very clear how I am using beta now. Because we have discussed IC minus IB is equal to beta. So IC is equal to beta into IB. It's the second step. What is the third step? Just calculate this current across this VC. VC is equal to IC into RC. Okay. Now what is IC now? IC is equal to 43 milliampere. IC is how much? 43 milliampere. Okay. Now, what is IC into RC VC? VC is equal to IC into RC. What is IC now? 43 milliampere. 43 milliampere into 1K resistor is equal to 43 volt. So VC is equal to 43 volt. You applied V. V is how much? 100 volt. And what is the drop here? 43 volts. So what comes here at V naught? We call V naught is equal to 100 minus 43, 57 volt. Now V naught is how many voltage? 57 volt. So V naught is equal to 57 volt. See how many steps? V naught is equal to V minus VC. You understand now 4 steps?
Sir, can you explain third step?
Third step, the current flowing through this is IC. So the drop across this is IC into RC. It's a Ohm's law. Nah? If there is a current, power current flows through a resistor, V is equal to I into R.
No, sir. What you have done after that last step, sir? 43 milliampere into 1K.
Yeah.
So it should be, sir, 43 ampere, no, sir?
Which one?
Yes, sir. Last one, sir. Milliampere into 1K. So 3 zeros are cancelled. So it should be 43 ampere.
1K ohm. I
Okay, sir. Okay,
into
sir.
R. What happened? 43 into 1. See, this has to be done like this. This I can do like this. 43 into 1. 43. M into K. This is 10 power minus 3
Yes,
into
sir.
10 power 3. Gone. 1. And next one is ampere into ohm. A into ohm is equal to V. That's why it's called 43 volts. It came 43 volts. Okay, that's the way. It's actually 1K ohm of I got to. Normally we don't write this. When you say 1K is 1K, but actually 1K ohm is a right representation. Thanks. Sometimes I do miss. I'm following just the industry what we follow. Okay, sometimes it's a mistake. I should write ohm here. Then only you understand. Some beginners may get confusion here. So it's good. So now what happened? If we erase all these things, steps, since you have everything on the steps. So you need to follow these 4 steps. Step 1, step 2, step 3, step 4. I will tell you once again how to do that. I have a transistor. First, I draw only what is required. I draw only RB. I draw only VB. And across this is VBE. So we find IB first. Okay. That is the easiest way to start finding things.
Sir, in PNP, what are the steps, sir?
Almost same step. You have to do the other way. The thing is current will flow this way. Otherwise, same beta, everything is same. The current will flow like this. There's no difference at all. Basically, how do you draw the circuit? That's the only thing. Now we have found this. Now, this is the first step. So first step is this, IB. IB is the first step. Understand? What is the second step? Second step is find out IC. This is a beta, is we know. IC is equal to beta into IB. That is the second step. So finding IC is the second step. And third step is we have a resistor called RC. And we should find out the voltage difference across this. So IC into RC is equal to VC. This is called B, but B is a very confused one. That's why what they wanted was they start, see, already this is called VC, collector voltage drop. So what they have done was, and for example, if you put a resistor here, they call this as a VE, voltage across the emitter thing. So I can do that. There's nothing wrong. There are circuits, they put the resistor at the emitter also. Now the trick here is they put a name, this is a VCC. They add one more C. That's why the name VCC came, because this became VC. So they wanted to do this. That's called, they call VCC. That means you are applying at the collector. There's no other expansion or anything. They just gave a name called VCC. Okay. There's nothing called equivalent called VE. There's called only VCC. So understand that now. That is what we calculate. Now I do a small change here. The same circuit. We did a calculation. We did a what calculation? First calculation, we found IB. It's equal to 4.3 milliampere. Then we calculate IC. Sorry, for 0.43 milliampere. IC is equal to 4.3 milliampere. Now, if we change the resistor, RC is equal to 2K. Then the voltage across will change 2K into 4.3. It becomes 8.86 volt. Sorry, I think there's a mistake here. I did a mistake. This is 4.3 only. So I put 10K, I thought so. 43. Into 2, it becomes, you get 86 volt. So you get here, how many voltage? 14 volts. V naught. If you apply here, VB is 5 volt and the RB is 1K. This is what we calculate. VB is no resistor. You cannot add. That's a transistor thing. You cannot change. You cannot add a resistor. You cannot add a resistor on VBE. VBE is always 0.7 volt in silicon. These are all transistor property. You cannot change it. That's a property of the transistor diode. The silicon diode is the thing that is having 0.7 volt. There is nothing called you add a resistor or anything. You cannot add it. That's why we are adding here RB. You can change the RB. If you change the RB, IB will change as per Ohm's law. But you cannot change VBE. VBE is always 0.7, which you cannot change. That is basically the behavior of your. Here you can add it. You can add. That is VE. That's called, they call VE, RE. Sorry, they don't call RBE. That is connected only to emitter. There's no base comes into picture. Because you asked that VBE. There's no base at all here. This is connected to only this one. You can add it. Yeah, there are circuits. They are called emitter followers and so many circuits. Go and check in your college. They will teach you only that. That if you want, I can take a separate classes. But that's not my intention. My intention is to teach you on embedded system programming, not this. Understand? So now I ask you one question. If I put 3K here, what will happen? You understand here? If I put 3K here, what is V naught? Anybody can tell me? If I put 3K, now IC is 43 milliampere. IC is how much? 43 milliampere. Now I'm asking, what is V naught? Can anybody? What is V naught? Understand? What is V naught? When RC is 3K, what is V naught? Anybody? Please. What is V naught when RC is 3 volts? VCC is 100 volt. VCC is 100 volt. Correct. Thanks. What is V naught? Beta is 10. Beta is 10. What is V naught? Minus 29 volt. Okay. I got one answer, minus 29 volt. Any other answer? Oh, 43 into 3K. 129. Oh, 100 minus. Fine. Next. Anybody else? I remember, I told you this is transistor is a resistor. That means that we connect two resistors now. And here ground. This is 0 volt. And this is 100 volt. And you say this is minus 29 volt. Do you understand that? Let me erase this. I'll write the equation slightly smaller. So I'll draw it bigger. So our as per our thing, this is 100 volt. This is RC. 1K, 3K. And here ground. You say here minus 29 volt. But always ground is 0 volt. Understand? If you remember the last class, we discussed this guy, the circuit worst case is short. That time this becomes 0 volt. Or it can be off. That time you get here 100 volt. So the output can be between 0 volt to 100 volt. And the output can never be in negative. Please understand. The output can be only between 0 volt and 100 volt. No way negative. This is not possible. If I say that between 0 and 100, you say in between is minus 29. That doesn't look logical. So what is the problem here? Anybody can tell me the problem? But you are given a minus 29. That's kind. Somebody has given a minus 29. That's as per calculation, it's correct. Now I ask you one more question. Here. I do not know the resistor here. I do not know the resistor. It can be 0 ohm or it can be infinity. Now tell me, what is the maximum current can flow through the circuit? What is the maximum current can flow through the circuit? Can anybody can tell me? What is the maximum current can flow through the circuit? I don't know this resistor. This can be 0 to infinity. What is the maximum current can flow through the circuit? I need an answer. Please. What is the maximum current can flow through the circuit? I don't know the resistor. This resistor can vary from 0 to minimum is 0. Maximum is infinity. What is the maximum current can flow through the circuit? Yeah. When R is 0 only, maximum current. Hundred by infinity is 0. Am I right? When this case infinity is the lowest current. When infinity means off, infinity is off. When it is off, the current is 0 ampere. That is, infinity means lowest current. IC, I minimum. I maximum is this. When this is connected short circuit, only I maximum. Now, when it is short circuit, what is the current will flow through the circuit? Tell me now. See, now you understand. Your problem is not with electronics. Your problem is with electrical. Your problem is you are not able to, these type of things. The problem is most of the ECE students get confused here. You are not very clear about voltage divider circuits or two resistor circuits. I ask you a very, very simple question. When R is 0 here, what is the current here? That's when R is 0 only, it's a maximum current. When R is 0, what is the current here? We know the voltage.
Sir, 0.03.
Why 0.00? 100 volt. And 3K, how much?
100 by 3000, sir.
How much? 0.03. That's correct. Yeah. Don't tell me an ampere. Tell me on milliampere. That'll be easy. It's about 33 milliampere. Am I right? So the maximum current flow through this itself.
Sir, 0.0003 milliampere.
How much?
No, sir. No, sir.
Oh, that is 0.003 ampere. It's 33 milliampere. You understand now? That is, let's write it like this. 100 volt divided by 3K. That is 100 volt divided by 3000 ohm. Volt by ohm is ampere. That's done. You subtract this. 1 by 30. 1 by 30. I can say multiply 1000, bottom by 1000. The 1 by 1000 is milliampere. So 1000 by 300 is 33. So 33 milliampere. These and all have to be very, I told you, every time you cannot use the calculator. You have to be very clear sometime. So you see here, whatever here, resistor it is, the maximum current can flow through the circuit is how much? 33 milliampere. Am I right? Not more than that. But as per your calculation, IC is how much? 43 milliampere. Understand? In this circuit, because of this is 3K, the maximum IC is how much? 33 milliampere. But you are finding out IC is 43 because you are used IC is equal to beta into IB. Am I right? Now IB is how much? We have calculated IB is 4.3 milliampere. So IC is, beta is 10. So IC is equal to 10 into 4.3 is equal to 43 milliampere. You have done all the calculations right. But unfortunately, you forget one important thing. Whatever it is, it doesn't matter. Whatever you calculate, this is all calculation. In reality, this current cannot be more than how much? 33 milliamperes. So what happens now? What happens now? Where is the problem? Where is the problem? Anybody?
Sir, it will collect 10 milliampere and it will store.
Where? There's nothing called store and dot.
Sir, in the
Nothing called store
collector,
and dot.
sir.
No collector, no storing and dot here. It's all correct. It's all correct. The trick here is this. Trick here is this. This IC is equal to beta into IB. This formula is wrong. This formula is valid Only if IC is correct. The beta value is not always 10. The moment it goes above 33 milliampere, then the beta value will come down. That is called, actually that is called, you know what is the name of that? It's called saturation. And before 0.7, that is called cutoff. And during this period, that is when the beta is active, that is called active. So the transistor is having three regions: saturation, cutoff, and active. That I'll explain to you now. I'll explain to you now. That is when it is cut off, that is off. The transistor does not conduct any current. So IC is equal to 0. IC is 0 because there is no base current. Because you are given less than 0.7, IC is 0. And second one is on. Is on. It's called saturation. It's called cutoff. Now IC is equal to IC max. What is IC max? IC max is equal to VCC by RC. That's the current. You cannot go beyond that. So that means that when IC is become more than IC max, IC is equal to IC max. Maybe confusing. Now I'll tell you what it is. If I say that in the last equation, we say that in our case, because of RC is equal to 4K, 3K, sorry, 3K, IC max is equal to 33 milliampere. Because VCC is 100 volt. So we have calculated IC max is 33 milliampere. Now IB is how much? 4.3 milliampere. Beta is 10. So IC is equal to IB multiplied by beta is equal to 43 milliampere. So what happened? IC become more than IC max. That is not possible. So IC is equal to IC max. IC can never become more than 33 milliampere. So if your calculation finds out that IC become more than IC max, put IC is equal to IC max. That's it. That is called saturation. Now, let us go to the third one. Third issue, that is a variable resistor. This is called on, saturation. This is called active region, called resistor, variable. That is IC is greater than 0, less than IC max. Understand? Greater than 0, less than IC max. So this, if you understand this three, you understand the transistor. And always don't forget this. People always get confused with the translation. That is, if IC is greater than IC max, IC is equal to IC max. IC cannot flow through that. Then how do you calculate the RC? That depends on the transistor manufacturer. Every transistor manufacturer will tell you that what is the maximum current it can take. For example, let us assume that I am a manufacturer of a transistor. I am a manufacturer. I have told you that my transistor IC max is 100 milliampere. He will say only 100 milliampere. Now, in your circuit, you apply here 100 volt. You apply how many, say 10 volt, let's say 10 volt. You apply how many voltage? 10 volt. So you should calculate the value of RC based on that. RC should be never, RC is equal to 10 volt divided by IC max. 10 volt divided by 100 milliampere. 10 volt, I can call it as a 10,000 millivolt. Milli volt ampere is ohm. So 100 ohm. That means RC should be always greater than 100 ohm. If you put the RC less than 100 ohm, what will happen? There will be more than 100 milliampere when the saturation. That time, the transistor will go bad. The transistor will go bad. So you should never supply more current than this is called rated current. Now people used to ask me, what is the job of hardware engineer? These are the things hardware engineers will do. When they do the board design, they will find out that nobody is drawing more current. They will put a resistor and everything correctly for that. Okay. So it's very clear. We can able to use a transistor as a switch, off or on. Or variable resistor. When I use a switch, we call this transistor. They give a different name. When I do cutoff and saturation, I call this transistor as a gate. The same transistor is called as a, when it's on active, called amplifier. The same transistor can be used as a switch or variable resistor. So based on that, how you are using it, we call them as a thing. If you are using a gate, we call that as a digital electronics. When you are going to use as an amplifier or variable resistor, we call it as analog electronics. So clear. I supposed to finish this class in the half an hour, because next half an hour I supposed to discuss about FETs and MOSFET everything, but unfortunately, fine, no problem. See, don't worry. We have to understand. We may take the extra class. That I don't mind to have an extra classes, but we have to understand this very clearly. Without there's nothing on going faster without understanding. That's why I thought I'll extend this. Next session, I'll discuss about FETs and MOSFET. What is the difference between current control and voltage control, everything. You understand this? So I can use the transistor as a switch. So please understand this. Normally, don't get confused between the gate and main. Collector and the emitter. This is a main circuit. We can draw like this. This is a main circuit. Gate is only a control. Gate only controls. That's why normally people now you're finding it out. When I use the IR, from here only this gate we derived as on and or not. From there, we proceed to the combination everything that you can watch the digital electronics classes videos. Understand now? So you understand the big difference between digital electronics and the analog electronics. The applications of this are all so many things, amplifiers. voltage regulators, all those things. And this application is gates, logic functions. Okay. If you have any doubt, you can ask me now before we break. Okay, then let's take a break for about 5 minutes. Then we'll come back and discuss about the effect and everything. It's all very simple. If you know the formula, IC is equal to beta into IB. There are two things you have to remember. You have to remember these 4 steps. First, calculate IB. IB is equal to, sorry, I'll share the board. The 4 steps you have to remember. Then you will do wonders. Any analog VCC. One is IC is IB is equal to VB minus VBE divided by RB. This is step 1. Step 2. IC is equal to beta into IB. Step 3. Here only is the problem. Here, after IC is equal to beta into IB, you have a small step. If IC is greater than IC max, IC is equal to IC max. Please understand this step. Normally, we write the step 2, but we generally forget it. Correct. Yeah, you are right. That is when somebody has asked that when VB is 0 volt, then the transistor is off and VB is 5 volt, transistor is on. That's perfectly right. That's why we are using on digital. The 2 voltages. Then VC is equal to IC into RC. Then 4th, V0 is equal to VCC minus V0. This all. Only 4 steps you have to remember. Nothing more than that. Is it clear? I hope it's clear. So let's